So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be talking about the Rust borrow checker and specifically the kinds of rules that you can help to build your intuition as to how to work best with the borrow checker. Now, before we get into it, I would like to say that if you enjoy this kind of tutorial and you want to see more of it, please do make sure to subscribe to the channel as it really does help out a lot. Turn on notifications so you're notified whenever I release videos just like this one today, and go ahead and leave a comment down in the comment section below if you have any questions, suggestions, or feedback. Apart from that, if you like the video, please do make sure to like it as well. Now, first of all, what is the Rust borrow checker? If you've seen some of my other videos where I've touched on the idea of the Rust programming language, the borrow checker is what makes Rust so unique. It makes it so that Rust can enforce the ownership rules upon memory that it does. It makes it so that Rust can do completely automatic memory management, but it does so at compile time, also verifying memory safety for your applications as long as you don't use any unsafe blocks. It'll verify, for example, that you don't use a variable after it's been freed. It'll verify that you don't have two separate functions with mutable references to the same data, just in case there's a data race, or one of them doesn't expect something to be mutated a certain way. It'll make sure that multiple threads cannot have references, especially mutable ones, to data unless they've been specifically marked as being safe to send across threads, and so much more. Now, these safety guarantees are only possible because of the Rust borrow checker. And even though it does make programming in Rust quite convenient because of the guarantees that it gives you, it does also introduce some complexities. Particularly, there are a couple of data structures that are very difficult to implement in the Rust programming language. The most notorious example is a linked list. Implementing linked lists and actually using linked lists in Rust is very difficult, especially for beginners, just because of the inherent fact that every single node has to have some sort of reference in a way and own the other nodes in the chain. It is a little bit difficult to sort of wrap your head around. Other programming languages don't have this problem because either they're like C and they have you manage the memory yourself, or they're like Swift or Python or Java or whatever else, and they use automatic reference counting or garbage collection to, at runtime, determine when nodes no longer have any more references, or if there's just cycles of references and automatically free their memory. So let's go ahead and take a look at the Rust borrow checker and learn some of its quirks and how it determines things like lifetimes using some linked list examples. Let's take a look. All right, now I want to start off by talking a little bit about why I think this is an important concept to cover. And to start off, let's take a look at a little bit of Swift code. So Swift is, a pretty standard programming language, I guess. It has a couple pretty innovative features. Like, in my opinion, its generic system is very powerful, a lot more powerful than most other languages. It's much more flexible. The syntax is really elegant, things like that. But the part about Swift that is also pretty unique is its use of the automatic reference counting system. So what that means is that while most programming languages are garbage collected, so for example with Python, it'll track the number of references for every object, and then every once in a while it'll pause your program to collect garbage, deallocate memory, and continue. Swift does that in real time. So every time a reference count increments or decrements, it will immediately determine at that moment in time whether or not that variable still needs to exist, and then deallocate it if it doesn't. That has advantages and disadvantages, but that's not the point of the video. The point of this video is to talk about guarantees. So let's take a look, for example, at this linked list class, right? So in Swift, classes are reference types, which is why we need to make the linked list a class, because it contains itself and structures can't do that, otherwise they have infinite size. We have a generic type T, which is the kind of data we put in, super simple append function, super simple print list function that do exactly what the name suggests. Then I have functions like this. So, for example, yield pairs. What yield pairs does is, given the linked list of, for example, 1, 2, 3, 4, 5, it'll call this function that you pass it on the pairs 1, 2, 2, 3, 3, 4, and 4, 5. Now, what's really nice about the way that Swift implements, and pretty much every other really compiled language implements its features like this, is that they help you in code define an API contract. So what that means is, for example, this function must expect variables of the same type as within linked list. And when you create this closure in line and you pass it to this function, at compile time, Swift will verify that whatever you're doing to these variables within that function are compatible with the variable type within the linked list, right? That's something that Swift will ensure at compile time. Doesn't matter if you're passing in a structure, doesn't matter if you're passing in a class, doesn't matter if you call this function inside of another generic function that has protocol restrictions on T, whatever, right? It'll verify that whatever you do conforms to the contract of all of these different types at compile time, right? And it'll do the same thing for the linked list. Like for example, we have features, like for example, we can say that data is supposed to be immutable. So within every node, you're not allowed to have a mutable piece of data. Now this is very helpful because in large code bases, it becomes incredibly annoying to deal with parts of code that don't have a well-defined contract. Think about Python. A lot of people think, Python's a really simple programming language and it's easiest to build things in Python. But believe me when I tell you that when you start working with code bases that are even medium to large in size, that very quickly breaks down. Because in Python, if you want to make a change to some part of a code base that you're not aware of, or that you're not familiar with rather, you have to rely on two things. You have to rely on human-written API contract documentation, assuming it's even there, and they didn't just assume you know it. And then you also have to rely that everybody using your functions and types just happens to actually conform to that contract. Because with Python, thanks to duck typing, it's very easy to not do that. It's very easy to mutate internal state of classes that you didn't expect to be mutated. Whereas in languages like Swift or Kotlin or these sorts of languages, you can verify that these things will never happen. If I say it's let data, I know everywhere that that is never changed once it is first initialized. I don't need to look. Right? These sorts of guarantees make it super convenient to work with these more complex programming languages for larger projects. And that's why, for example, here in like the append sorted function, I can say, hey, if you give me a linked list where the elements of type T conform to the comparable protocol, meaning I can do things like this, then I can go ahead and append into the linked list in a sorted fashion, regardless of what the type of T is. And this is the kind of thing that in C++ is really annoying to do, because when you have templates, it's not checking these sorts of, protocol conformances and things like this. And so if you call this function with a template on the wrong type of linked list, suddenly you get an unparsable error message about using the wrong operator, right? And so, we've evolved to have better languages that can help you enforce these contracts more and more at compile time. We went all the way from C having almost none of it, some level, to C++ having, some more, I guess, some less in other ways, like with templates. And then we went, we have a whole different class of programming languages like Python that do duck typing, meaning do whatever you want. And as long as Python can figure out a way to do it, it'll let you. And then we have more strict languages like Swift that are, actually checking as many things as they can at compile time. And Rust is also in completely a different class of its own. It helps you enforce these kinds of complicated API contracts at compile time, but they do one more thing. They make it so that object and data lifetimes are also part of that contract. That is really interesting to me. So for example, here with Swift, with the yield function, the values of type T that you're passed, all of their memory information is insanely ambiguous, right? So if T is a reference type, then you would be passed references and you'd be incrementing a reference counter. If T is a value type, then you're going to be passed technically references of T, but then if you try and mutate it, Swift is going to do copy on write. And if you're passed like primitive types, then you're just going to be passed like copies immediately. Like, what is happening behind the scenes regarding memory is totally abstracted. And that makes it very easy to code, don't get me wrong, right? Like this sort of code is very convenient to write, just like how it's convenient to write Python code for small projects. But then once again, as you start to scale Python, you hit these problems with types and people not using your code as they intend. And similarly, as you start to scale this kind of code, you also get more issues like, for example, optimization problems, trying to understand why you have a bottleneck in your code. Could it be the reference counts? Could it be the fact that there's a tight loop that's calling a function that does very little work, but has to also increment and decrement a reference counter, right? Could it be the fact that copy on write isn't working properly, and even though you're not making any changes to your value types, you're still making copies? So there are all these things that are insanely ambiguous, and once you start to hit large projects with complex logic, it's super hard to debug. With Rust, though, all of this is specified directly in the signature of your function. Let's take a look. So if I go ahead and vsplit out into a similar Rust file that I have, as you can see, I'm basically mirroring the Swift code. So I have a structure of type linked list T. We contain a reference, an optional reference, that's what box is, to the next linked list node. And then I implement the same initialize, append, and print functions based on whether or not the type within the linked list conforms to the display trait. And let's go ahead and take a look at maybe like a Rust equivalent implementation of yield pairs. I think that might be helpful. So in Rust, the way I would go about doing this is we would start off with, of course, our function declaration. So we'd say fn yield pairs. And obviously, right off the bat, we need our generic type T. And we need to take in our linked list. But hold, right off the bat, there's a bit of a difference. We don't want to take ownership of the linked list because we don't need it. We're not doing anything with that memory. We're not mutating it. We're not getting rid of it. We just need a reference to that linked list, right? After that, we also need our yield function, which in Rust would be a generic type. So we would do f, and then we'd do where f is a function that takes two values of type t. You may think our function signature is over, but actually not just yet. Because, and here's a really interesting part about Rust, think about it. We have a reference to the linked list that owns data of type t. If we expect a function that's going to take two owned values of t, this is immediately invalid because we cannot do that. We cannot take ownership of data behind an immutable reference. That doesn't work. So we need to specify that there's references of type t, but we can't do that either because we don't know how long those references are supposed to last in this context, right? What if, for example, this function that you call with these references does something to drop the owned memory of the list that we were passed, and now all of a sudden these two immutable references suddenly are invalid, right? Whether or not that's actually possible depends, because if you're calling yield pairs, you probably wouldn't be able to drop the reference anyway. But point is, these sorts of edge cases can occur. And so this is the really special part of Rust. You can make the lifetime of this reference a part of your function signature. You can make it so that you can say, hey, when we're calling this function, this is what's called a generic lifetime specifier. It starts with an apostrophe, a single quote. Sure, we're being passed an immutable reference to linked list, but this will specify how long it has to last. And this will specify that the function we pass references of type t2 will make sure that these values last at least as long as the backing linked list behind it, right? That's the key difference that Rust lets us specify. The lifetime of the data is now part of the API contract, moving more things to compile time to make it as easy to disambiguate logic as physically possible. That's the idea. Making it so that large projects are easier to build. Now from here, we can go ahead and start mirroring our Swift logic. Now there are a couple issues with this, and we'll get to those because the Rust compiler should theoretically help us solve them. So if I were to just go ahead and do like a naive one-to-one translation of the Swift logic, we might end up with something like this. A dot data, b val dot data, a equals a dot next, and then we'd unwrap that, and then b equals b val dot next. There we go. So I'm going to go ahead and disable Copilot also, actually. Theoretically, I mean, you would think something like this would compile, but it actually doesn't. If I were to go ahead and try it out, there are a couple of issues we hit. One of them is the fact that, of course, yield function expected references, but we're passing actual data, which we're not allowed to move. So we go ahead and pass those references. We're going to compile again. Now it's complaining that we store in A, at first, an immutable reference to a linked list, but now we're unwrapping a box, an actual owned value, directly into it. Rust recommends we solve this by grabbing a reference to the box, which would make this valid syntax. But what Rust isn't realizing at this point is that we're not allowed to do that. The reason we're not allowed to do that is because if we were to grab a reference to the unwrapped owned value, that would mean that we are trying to grab ownership of a value behind an immutable reference. We can't do that. So instead we do .asRef.unwrap, which basically takes this optional value, gets a reference to it, moves the reference out from outside of the optional value to inside of it. So now we have an optional reference value, and then we unwrap that instead. So now we end up with an immutable reference to the box type within the optional that still conforms to this lifetime. If I go ahead and save that, compile again, we see two more issues. One of them is that, once again, we are trying to move out of list.next on line 41 because we're trying to access that member directly, which would give us ownership, but we're not allowed to do that, so we must get a reference. And similarly, over here, it's saying that, or I guess actually that error would not be relevant once we compile with this new change. So if I were to go ahead and save and run, we get a different error now, and that error is that over here it expects that we would be assigning a reference to an optional because of this, but we're actually passing it the optional directly because we're not getting a reference. So we can fix that with Rust's suggested fix, which is to grab a reference, and just like that, we're good to go. Our Rust code compiles and runs just like our Swift code. So if I go ahead and run the Swift code as well, I can show you that the Swift code runs the same. It creates a linked list of 1, 2, 3, 4, 5, and then yields these pairs. Now to take this a step further, let's work on, I guess, a more complicated function, the append sorted function as well, and take a look at what the differences are in how we would translate from Swift and how we follow the Rust compiler recommendations. Because as you can tell, a very large portion of the help that in helping us conform to the borrow checker's rules comes from the actual Rust compiler. It gives us really helpful error messages. Of course, they are wrong sometimes, because if they were correct all the time, then we wouldn't need the rules to begin with. That's why there's ambiguity. But if you understand the rules, they can help guide you to the right solution. Even if the suggestions are wrong, you'll be able to recognize that they're wrong and work on figuring out the correct ones. So let's go ahead and take a look at the append sorted function. The idea of it is pretty simple. The implementation can be a little bit complicated. Let's go ahead and take a look at it. So in particular because of the translation of the ownership rules, but we'll take a look at what that entails. So I'll just go ahead and move this down a little bit so we can sort of have a more aligned view of it, and let's start implementing. So let's just say we start off, of course, with our function declaration. So fn append sorted, snake case, not camel case. T conforms to ord in Rust is what it's called, not comparable. This time we are actually going to take ownership of the linked list. And of course, we're going to make this optional. And once we've got that, let's go ahead and also take the data that we want to insert. We're going to return the linked list once again. The reason we're doing this is because we may want to change the head of the linked list, in which case we return a different value. Now, if we go ahead and get the old head from the list, we have different logic. If there was no old head, so we're just literally creating a new linked list node, then all we got to do is return linked list new data. So that's all there is to it. Otherwise, there is some more complicated logic for us to follow. So let's go ahead and start implementing it. First thing we're going to do is we're going to create our new node that we want to actually insert into the linked list, because at some point we know we're going to need it. We might as well create it now. So we go ahead and create the linked list node. Then we're going to check to see if we're in the right position. So if right off the bat we're in the correct position and we know that we need to replace the old head, then we go ahead and set the new node's next value to the old head, and then we return the new node as our new head value. Otherwise, if that is not the case, then we have a loop that we use to determine where to insert this new node in the linked list. So we start off by setting our current value to old head, which is a very typical way of doing this sort of like linked list sort of traversal, and then we just do while let sum next equals current.next. From there, we go ahead and do if next.data greater than equal to data, so check if we're in the right position. If we are, we can break. Otherwise, we set current to current.next. And then after that, we simply do new node dot next equals current.next, current.next equals new node, and then we return our old head. You would think this would work, but unfortunately it does not. I'll tell you that right off the bat, because there are a couple of issues. As a matter of fact, to sort of prove it to you, let's go ahead and compile our Rust code. As you can tell, it complains a lot. One of them is, starting off here at the end, is the fact that it expected an optional value to be inserted into next, but that we inserted an actual value. That is not compatible. It also, same thing here, it expected, or rather the opposite, I guess, it expected an actual linked list, but we gave it an optional box, right? So it's complaining a lot. So let's go ahead and start debugging what some of this means. Let's start off with this one, I guess. So this one says that it expected us to put like an actual linked list type into the current variable, but we put an optional box, right? So if we take a look here, this is being set to old head, which is a linked list type, an owned linked list type, and we're giving it an optional box. In order to make these compatible, we have to grab a reference to the old head here, and in particular, we're actually going to need a mutable reference because we do end up changing it down here. And here what we can do is grab, we would do something like asref, but asref gives us an immutable reference, so we do asmute, and then we unwrap it, right? Because this bit of code told us that there is indeed a next value, so we can assume that it is safe to forcefully unwrap, and asmute makes it so that what we unwrap gives us a mutable reference, right? So then this is now compatible because the mutable reference to the box is the same as the mutable reference to the type in this case. So that bit of code is now all peachy and happy, it likes that, the borrow checker is satisfied. Now, Rust is complaining that it doesn't like the fact that we are passing it this value directly instead of making it an optional. So let's go ahead and solve that for Rust. Let's make it some current.next, some new node, and let's see if that works. Rust didn't like that either. Why didn't it like it? In this case, it's because it expected boxes inside of the sum. As you can see, clearly this logic isn't exactly correct. So how do we make it correct? Well, if you think about what exactly Rust is asking us for here, right? It's asking us to give it an owned box representation of linked list T wrapped in option, right? And we know that we need to set new node next to current next. So what we do is we call the take function on current next. What this will do for us is it will give us ownership of something behind a mutable reference. I know I said we can't get ownership of things behind references, but this is different. What the take function will do is it will swap out what's actually in next for its default value. Now, what is next? Next is an optional value. The default value for an optional is none. So what take will do is it doesn't violate any rules. It's still following all the Rust rules. But what it does is it takes this mutable reference to current next that we have, and it makes it so that we swap out current next for a none value, and take returns to us the owned version of what was originally inside of current next. And now that we own that box representation, we can go ahead, wrap it in some, and put it into new node next, and it shouldn't complain about that bit anymore. Now, similarly, we now have current next that is set to none, but we don't want it to be set to none, we want it to be set to new node. So we can replace the inner value of the optional container with a box representation of the new node, right? Because that's not something that we created before. We need to box the node in order to make it the next value for our current node in the loop. So just like that, we are able to compile and we get different errors. In this case, it expected struct box, but it found option box, which would make sense because when we take this, we are actually taking the optional box representation from the raw mutable reference. So we actually don't need to wrap that in sum. Now we get one last error, and that is that it expected enum option, but actually found linked list for new node.next equals old head, and that's on line 57. And to fix this, we just go ahead and make sure that we use a box representation, or we could actually even use the replace function here. So we could do new node next replace box new old head. And so that makes it so that the next node after this new head is a box representation of the old one. We do get a few more errors. For example, the fact that Rust over here is complaining that new node is being mutated even though it's an immutable variable. So we can fix that, say that it is a mutable variable. We didn't need to say that in Swift because it's a reference type, so we're technically not changing it, but Rust doesn't care. This is a value type according to Rust, and so we need to mark it as mutable in order to set its next values here and here. Let's see what else Rust complains about. After that, it complains about the fact that we are using the data variable multiple times, right? Think about it. If we go ahead and pass data to LinkedList new, LinkedList is now what owns the data. We can no longer compare against it because the ownership has been moved away from this function. So in order to actually properly compare, we would need to do new node.data here, and same way, new node.data. That fixes that problem. From there, here Rust is complaining that we are moving the next value of the current node out of the node into this next variable here during the loop. And so in order to fix this issue, we can tell Rust that we expect to get a reference to the current next variable instead of the actual owned variable. The reason that this fixes the problem is that this is fine just being a reference because we're only comparing. And after this point, we no longer use this reference. We go ahead and look at current next over again using asmute over here. So after this, because this reference isn't used, it's effectively invalidated. And then this line of code is also allowed to run properly. And then over here, it's complaining because we attempt to get a mutable reference to old head, even though old head is an immutable variable that comes from an if-let statement. So simply making this mutable should fix our issue. And just like that, our Rust code compiles and then runs. And if we go down here and we swap out our append calls for sort append calls, 1, 5, 2, 4, 3, even though the order is wrong, it should still help us output in sorted order. And just like that, we've implemented our Swift functions in Rust, and the way we did it made it so that all of our variable lifetimes were known at compile time. No memory management had to occur at runtime. That is why I love the Rust programming language so much. It is really powerful. Generics extend beyond just types, and I find that very fascinating. Now, there is so much more that I want to dive into, but this is already a lot for a video. So there's going to be more videos on Rust, why it's special, and special things you can do with it in the future. Make sure you subscribe to stay tuned for that. Turn on notifications so you're notified when I release those tutorials. Like the video if you liked it, and any questions, suggestions, or feedback, feel free to leave them down in the comment section below. Thank you very much, everybody, for joining today. Goodbye.